Hello, this is week one. We are going to look at the introduction and the introduction to the universe. So I will share my slides and we can begin. This is okay, there we are. So in this section of class, we're going to be looking at the rocks and minerals of Earth. And so I always like to start at the very beginning so you can see what we are sort of starting with. And you'll see some of the resources in class this week have to do with these resources, such as the reason why barns are painted red and the oldest color in the universe. I hope you enjoy some of those. So looking at the creation of the universe, the universe was created about 15 billion years ago. And the currently accepted theory is that all matter and energy was at a point, and by a point I mean about 200 miles in diameter. And it exploded and blew up, and it's been expanding ever since. And so when you hear about the Big Bang theory and the Big Bang, it's not that there was some explosion that happened and then everything is hunky-dory. It's all bang. We're living inside of a giant ongoing explosion. Like if you see on TV an explosion of a car, we're living inside of that. And the universe is expanding. We know that it's expanding because when we look out at distant stars, light is shifted towards the red end of the spectrum. It's called redshift. And by way of analogy, it is similar to what happens with the Doppler effect. So if you hear a motorcycle coming towards you, you hear, right, as it's coming towards you, the sound shifts in tone. And then as it goes away from you, you hear, and it's not that there's this cyclical, that's going on as the motorcycle is driving down the street. It's that sound is shifted as the source of the sound moves towards you or away from you. And it's the same thing with light. So we know that the universe is expanding because light is shifted towards the red end of the spectrum. And for a long time, we thought that this was going to just keep on happening. The universe is going to keep expanding forever. But then we realized there were pieces of matter that we didn't realize were in the universe, dark matter, black holes, things like that, that actually have gravity. So now the theory is that the universe will reach some sort of gravitational maximum. Don't ask me what's on the other side of that because I don't know. And then it will start to come back onto itself and contract. And we will know that that is going to happen, or that is happening, because then instead of light being shifted towards the red end of the spectrum, it will be shifted towards the blue end of the spectrum. That will be called blue shift, and the universe will crunch back down onto itself. And there's some theories that say that this has happened 6 times in the past. So it expands, contracts, expands, contracts. So that's the universe. The Milky Way galaxy is sort of next down. So we have this galaxy that's between 100 and 200 billion stars that are in this rotating galaxy. It's flattened, and there's this central bulge where most of the matters, most of the stars, and then there are these 2 spiral arms, and it's slowly rotating around. We're about 3/5 of the way out one of the arms, a little insignificant planet orbiting around a little insignificant star as the matter trails off in our galaxy. So when we go down to our solar system, the sun and the planets that rotate around the sun, we are in a second generation situation. So we had a first generation star made of mostly hydrogen and some helium and all the planets as well. And that star burned out, exploded, and became something called a solar nebula, a solar cloud. And it was this big ball of dust and gas. Now, the gravitational attraction of particles started to exert its force on this cloud. 2 particles slammed together, 2 more slammed together. So the whole thing started to rotate, flatten, and from this cloud of dust, the central sun, hydrogen and helium still, and then the other planets were formed. So it's kind of cool because when we look next week at the periodic table of the element, you'll see, or this week, you'll see that the naturally occurring element in the periodic table actually happened because of nuclear reaction. So not just rocks and dust slamming together, but actually atoms slammed together at the atomic level. And we grew from hydrogen and helium to lithium and carbon and hydrogen and nitrogen and oxygen. So all the cool stuff that we're going to look at for the rest of the semester happened during this transition from the first generation star to a second generation star. And now we have the sun with these 8 planets. Used to be 9 planets. There should have been 10 if Pluto is a planet. On the other side of Mars, there's a failed planet. So this rubble that's going around in the asteroid belt that failed to sort of get its act together in terms of a planet. So we should have 10, I guess, if you wanted to count Pluto. So dropping down again, you learned this since kindergarten. You have the sun and you have the planets. First 4 are terrestrial planets, so they're rocky, and the last ones are Jovian, so gas giant. They're composed of ice and gas. And as we go out, you see Pluto out here. Pluto doesn't trace within the sun's equatorial plane. It has this elliptical orbit. It got kicked out. So there you go. There's our solar system. We drop down one more and we have Earth. And Earth is a fascinating planet. In some ways, it's an average terrestrial planet. In other ways, it's fascinating. It is unique in the solar system in that it has appreciable vast quantities of liquid water. It's the blue planet. So 1.36 billion cubic kilometers of water cycling around on Earth. It's rocky. It has tectonic cycles too that we'll briefly mention when we look at the rocks in the next lecture. And what else? There are these cycles. It's a very dynamic planet, has an atmosphere. So talking about the atmosphere and talking about the oceans, you may know of Earth as having 3 layers, right? Or maybe 4, the core, the mantle, the crust, or it's subdivided into the core, the inner mantle, the outer mantle, and the crust. And so those are things that layered out again because of gravity. So once Earth was finally finished being formed, more or less in its size from planetary accretion, asteroids hitting onto it, growing it from a speck of dust to a golf ball to a basketball to, I don't know, a physio ball, whatever, as you get bigger and bigger, then gravity, the center of Earth's gravity, as you know, is in the center of Earth. So as we'll see in the last slide, gravity pulls the most strongly on the things that are heaviest. One of the parts of gravity is that it's proportional to the product of the masses of the objects. So what happened is that the stuff that was the heaviest, iron and nickel, got pulled the most strongly and became this core of metal. It should be liquid because it's so hot, but it's forced by the crushing weight of the overlying materials into a solid. So you have this solid metal ball, and then you have the mantle, and people call the mantle liquid. It's not really liquid, it's almost solid, but it's just a little bit of viscosity enough that it can flow slowly. And that is what makes for plate tectonics. So that's also iron and nickel, but it's iron and nickel that's been complexed with silica, which is lighter. So it got pulled, but it got pulled less strongly. And then you have the crust, which is mostly just a silicate shell with a whole bunch of other little, impurities of the things that we mine and that we look for. So you have iron and nickel, silicious iron and nickel, and then you have silica. And then the stuff that was lighter, so light that it is in vaporous or liquid form at Earth's surface temperatures and pressures, got outgassed through volcanoes. It's hypothesized that plate tectonics was very active early in Earth's history, and these volcanoes, as part of tectonics, were spewing out all of these elements. And these elements then became our atmosphere. And as Earth started to cool, we're about midway through our cooling history, rain fell and became the hydrosphere. So we really have 5 layers: core, mantle, crust, hydrosphere, atmosphere. And we'll spend some time looking at the atmosphere when we look at geoengineering and climate change. So again, Earth is unique in that we have these cycles. We have the rock cycle, and we're going to spend a lot of time looking at the rock cycle in the next couple of weeks. You know that there is sedimentary, igneous, and metamorphic rocks. And maybe you know that these things are always, because of the dynamic nature of Earth, both from beneath with tectonics and above from atmospheric processes, weathering is always going on and magma is always welling up to the surface. So you have, there's not really a start here because it's a cycle, but it's convenient to start in the liquid part because one of the definitions of a rock, as you'll see, is it has to be solid. So this magma comes up and cools, and that's igneous. And then if it's exposed at the surface, it can weather, and you can see weathering transport deposition. You'll see that next time. And as that gets buried progressively, it will get metamorphosed. If it gets buried so deep that it melts, it becomes igneous again. You can also have igneous rocks metamorphose. So these rocks, because of tectonic processes and atmospheric processes, are always turning into a different type of rock. We also have the hydrologic cycle, which I mentioned before. We'll spend a unit talking about water quality, water quantity, and for your favorite object, you're going to look at how much water is involved in this. So again, 1.36 billion cubic kilometers of water cycling around on Earth. It's an exogenic cycle. That means it gets its energy from elsewhere, and that elsewhere is the sun. And so you see that water, most of it's in the oceans, long residence time in the ocean, it'll evaporate, becomes clouds, becomes hurricanes, tornadoes, the things that are in our atmosphere, rains and snows down onto the surface of Earth. And that will sometimes infiltrate lots of water in groundwater. Most of the fresh water on Earth is in groundwater, as we'll see, and then it cycles around again and again. We have biogeochemical cycles. Don't get too hung up on this for now. Bio, life, geo, earth or rock, and the chemicals on Earth, periodic table, right? So you have different elements. This implies there's a sort of bookkeeping that is possible as we trace nitrogen, phosphorus, carbon from the Earth to the organisms, to the atmosphere, to the water, to the plant, and then back to the Earth. So that goes around a lot, mediated by both solar energy and also the water cycle. Some of the ones that we're going to look at in this class are the carbon cycle when we talk about climate change. This is central here, human emissions here. There's a lot of things that go on that are natural that cause carbon to be shifted from the oceans, the atmosphere, to the rocks. Nitrogen cycle will be interesting and important when we talk about agriculture. So we have atmospheric nitrogen that gets fixed not by plants, but by microbes, bacteria. And then when it's fixed, plants can use it. We have animals that need it by eating the plants or eating animals that eat plants. And then things die, get decomposed, and cycle back around. So that's important, as is the phosphorus cycle, mostly when we talk about agriculture. Phosphorus is interesting because it doesn't have an atmospheric phase. It only has a ocean and rock and organisms. So you can see here, and you can pause the video if you want to see where phosphorus goes. So we'll revisit this when we look at agriculture, and it's not my intent to give you a intensive look at all of the things in this this presentation. This is really just an introduction to Earth itself. And then we have the tectonic cycle. The inside of Earth is hot. Why is it hot? Well, first, because of the asteroidal impacts. When Earth was growing, remember in planetary accretion, these asteroids are streaking through Earth or through the atmosphere, not the atmosphere, through space at 650,000 miles per hour. And that is tremendous energy of motion that suddenly stops. And you can't create or destroy energy. So it gets transferred from kinetic energy, potential energy to kinetic energy. So motion energy to heat energy. So that is one reason why it's hot inside Earth. Also, because when this was happening and as we were transitioning from a first to a second generation star, remember the atoms were slamming together and growing heavier and larger elements. Some of those are radioactive. So there's radioactive material inside of Earth. We'll look at that when we talk about energy. And for example, where to put spent nuclear waste. And then also heat of contraction. So as Earth, was formed, it's now sort of pulling in on itself. It's pretty much done with that, but the squeezing causes frictional heating. So we have heat inside. Again, we're about midway through our cooling history. And then the outside is cool. So now you have a gradient where you have the more dense stuff, the heavier stuff on the top, and the less dense stuff in the middle. So that creates these conveyor belts. And, if you want to learn more about that, you can take a class in natural disasters. I have some supplementary lectures. Send me an email and I'll send them to you if you want to learn a lot more about plate tectonics. But essentially what that means is that there are places where Earth is getting bigger because magma is welling up and making new Earth. And there are places where Earth is getting smaller. See in this picture under South America, because one plate is diving down, melting, and it recycles. And I already told you this. This is why the inside of Earth is hot, because of the decay of radioactive elements, because of gravitational contraction. I tried to draw these pictures of squeezing in on itself. And then the impact of asteroids. And the governing force that we're going to look at a lot in this class, not a lot, a certain amount, especially when we talk about energy, is gravity. And gravity, the equation, which I didn't write here, gravity is equal to the universal gravitational constant multiplied by the product of the masses of the two objects, and then divided by the square of the distance. It's proportional here, the square of the distance between the two objects. So if that's too much too quickly, all you have to think about is, for example, tides. So the tides are due to the gravitational pull of the moon and to a lesser extent the sun on Earth's deformable liquid water. And so the sun is much bigger. So if we just went on that first bullet or the third bullet here, gravity is proportional to the product of the masses. The sun is massive. And so there should be most of the water moving towards the sun. And the moon is puny, but it's really close to us. So it turns out that the predominant pathway by which water is deformed on Earth is because of the moon, because the moon is much smaller. So for that first bullet, proportional to the product of the masses, it loses. But where it's inversely proportional to the inverse square of the distance between the two objects, the moon's really close, sun's really far away. So that is gravity, and there they are all together. There's the equation. Gravity is equal to the universal gravitational constant, 6.6. If they make you memorize this in any engineering class you take, 6.67 by multiplied by 10 to the negative 11 cubic meters per kilogram per square second. And there you see those, you don't have to work with this, but the constant product of the masses, and then the inverse square of the distance. So that is a force that holds everything together in our universe and certainly on Earth, but it also does some tearing of things apart. If you look at natural disasters, you'll see how gravity pulls things apart. So that is our first unit on the introduction to the universe. And next time we're going to be looking at rocks and minerals.